At 10% of the speed of light, the nearest star stops looking impossibly far away. Alpha Centauri is a little more than 4 light-years from Earth. A spacecraft already moving at 1/10 light speed would cross that distance in roughly 42 years, ignoring the time required to accelerate and slow down. For the first time, an interstellar journey begins to fit inside something resembling a human lifetime. That sounds like the breakthrough. It is also where the real problem begins. At 30 million meters per second, the spacecraft is no longer moving through the environment we associate with ordinary spaceflight. The region between the stars is extraordinarily thin, but it is not empty. It contains hydrogen, helium, heavier atoms, charged particles, and microscopic grains of solid material. At conventional spacecraft velocities, much of that material is an almost invisible background. At 10% of light speed, velocity changes what every collision means. An atom cannot be persuaded to move out of the way. A dust grain does not need to be large to matter, and there may be no warning. The spacecraft is crossing nearly 30,000 kilometers every second. Light itself travels only 10 times faster. By the time an obstacle close enough to be detected becomes a navigation problem, avoidance may already be useless. The first misconception about fast interstellar travel is therefore surprisingly simple. Speed does not merely shorten the journey. Speed changes the environment. Researchers studying relativistic spacecraft have modeled collisions between high-velocity vehicles and the interstellar medium. Work motivated partly by concepts such as breakthrough starshot has found that bombardment by gas atoms can damage spacecraft materials, while dust impacts can cause erosion, melting, and explosive vaporization near the exposed surface. The severity depends on velocity, material, local interstellar density, grain distribution, spacecraft geometry, and shielding. Those studies usually consider tiny robotic vehicles because a gram-scale probe is vastly easier to accelerate than a crude starship. That difference is where this investigation begins. A probe can lose a surface layer and continue functioning. A starship carrying people cannot treat its forward structure as disposable unless the entire vehicle has been designed around that fact. Behind the leading surface could be thermal systems, sensors, propulsion hardware, communications, pressure vessels, electronics, stored materials, and eventually biological passengers. Protecting them requires mass, and mass is the enemy of acceleration. Consider a spacecraft with a mass of only 1 metric ton, far smaller than any plausible crewed interstellar vehicle. Giving that 1,000-kilogram object a speed of 10% of light already means placing roughly 4.5 times 10 to the 17th joules into its motion. That is only the spacecraft's kinetic energy. It does not include inefficiencies in the propulsion system. It does not include the infrastructure required to generate the energy. It does not include whatever reaction mass might be necessary. And it does not solve the problem of stopping. A ship that reaches Alpha Centauri at 10% of light speed, but cannot decelerate, has not completed an interstellar voyage. It has completed an extremely fast flyby. For settlement, extended exploration, or entry into orbit around a destination, much of that velocity must eventually be removed. So the same speed that was expensive to create becomes an expensive problem at the other end. That produces the first major trade-off. Go slower, and the energy requirement falls, but the mission becomes longer. A longer mission means life support systems must operate longer. Components must survive more years. Radiation exposure accumulates for more time. Stored equipment ages. Closed ecological systems have more opportunities to drift away from equilibrium. A crewed mission may cross generations rather than careers. Go faster, and some of those time-dependent problems become easier. But the kinetic energy problem grows. The impact problem grows. Shielding becomes more important. And every kilogram of additional shielding becomes another kilogram that must be accelerated and eventually slowed. NASA-backed studies of possible interstellar flight architectures have explored directed energy concepts precisely because conventional propulsion makes the mass and energy problem so severe. Instead of carrying all the energy source aboard the spacecraft, a powerful external beam could accelerate a lightweight sail from the home system. Concepts in this family have examined velocities reaching substantial fractions of light speed for very small payloads. NASA, but a laser-driven wafer and a human starship are not different versions of the same engineering problem. They occupy different worlds. A gram-scale probe does not need drinking water. It does not need an atmosphere. It does not need radiation shelters for decades. It does not need hospitals, food production, replacement machinery, or a habitat large enough for people to remain psychologically functional. Most importantly, it does not need to keep an entire civilization support system alive when Earth is several light years behind it. At 10% light speed, a starship halfway to Alpha Centauri would be more than 2 light years from home. A message asking Earth for help would take more than 2 years to arrive. The reply would take more than 2 years to return. 4 years is not technical support. The ship must repair itself, and this changes the meaning of reliability. On Earth, machines survive partly because damaged components can be replaced by an industrial civilization surrounding them. A failed pump can be manufactured somewhere else. A corrupted computer can be replaced. A medical supply can be delivered. Expertise can be called in. An interstellar starship carries the factory, the hospital, the power station, the atmosphere, the water system, the spare parts warehouse, and the people depending on all of them. Failure is no longer local. Systems become coupled. Make the shield thicker and propulsion pays the price. Increase propulsion power and thermal management becomes harder. Add redundant machinery and mass rises again. Reduce mass and redundancy disappears. Slow down to protect the vehicle from impacts, and the life support system must survive longer. Speed up to reduce the mission duration, and the material striking the bow becomes more energetic. There is no single engineering problem called interstellar travel. There is a loop. Every solution changes another part of the spacecraft, and the interstellar medium is only the beginning. Studies of high-speed probes have also examined spacecraft charging as particles strike the vehicle. A charged spacecraft moving through interstellar magnetic fields can experience forces capable of changing its trajectory or orientation, creating yet another problem for navigation and attitude control during a journey lasting decades. Other work has examined radiation generated when energetic interstellar particles penetrate shielding and deposit energy inside spacecraft materials. A shield can stop particles, but stopping them does not make their energy vanish. Their interactions can produce secondary radiation and damage electronics behind the surface. This is the deeper pattern we are going to follow. At ordinary speeds, empty space looks forgiving. At interstellar speeds, it becomes an engineering medium. Atoms become radiation sources, dust becomes an erosion problem, protection becomes propulsion mass, distance becomes maintenance time, acceleration creates a deceleration problem, and a spacecraft built to survive one constraint becomes harder to protect from another. So the central question of a real starship is not simply whether physics permits us to reach 10% of light speed. Known physics does not place a barrier at that velocity. The harder question comes after acceleration. Once a machine is moving that fast, can it remain a machine? Can its forward structure survive billions upon billions of impacts? Can its electronics survive the radiation environment created partly by its own velocity? Can enough shielding be carried without making propulsion impractical? Can heat be rejected? Can damage be repaired? Can a crew survive for the decades still required to cross even the distance to our nearest neighboring stars? And after solving all of that, can the spacecraft slow down? At 10% of light speed, Alpha Centauri is no longer separated from us by an incomprehensible travel time. It is separated by something more interesting, a chain of physical trade-offs with no obvious place to break it. The first of those trade-offs begins with something so small that at rest you might need a microscope to see it. A grain of interstellar dust. A grain of dust does not have to be large to become dangerous. It only has to meet the spacecraft fast enough. At 1/10 the speed of light, a ship moves about 30,000 kilometers every second. In the time it takes a person to blink, it travels thousands of kilometers through interstellar space. Almost all of that distance contains nothing solid. Almost. Interstellar dust represents only a small fraction of the matter between stars. Most of the medium is gas, dominated by hydrogen and helium. The solid component is thinly distributed through enormous volumes, with many grains far smaller than anything visible to the unaided eye. At low velocity, that sounds reassuring. At 30 million meters per second, grain size stops being the only quantity that matters. Kinetic energy depends on mass. It also depends on velocity squared. That second term is what turns something microscopic into an engineering problem. Take an unusually large grain with a mass of about 1 microgram. At ordinary speeds, it is almost irrelevant. At 10% of light speed, its kinetic energy is roughly 450,000 joules. The grain is still microscopic by spacecraft standards. The energy is not. And this is not the energy of an object gently striking the hull and leaving a small dent. The impact happens so quickly that both grain and target material can be heated, fractured, melted, ionized, and converted into an expanding cloud of debris and plasma. The front of the spacecraft does not simply get scratched. It can be locally excavated. This is why engineers studying relativistic probes think in terms of erosion and sacrificial pro material rather than ordinary micrometeoroid protection. The shielding used on spacecraft near Earth gives a useful comparison. Many vehicles protect against small orbital debris with layered structures. A thin outer sheet allows an incoming particle to strike and fragment. The fragments spread before reaching deeper layers, distributing the energy across a larger area. At several kilometers per second, that technique can be remarkably effective. At tens of thousands of kilometers per second, the regime is different. The collision becomes so energetic that the projectile and part of the shield behave less like intact solids and more like a rapidly expanding high-temperature event. Adding another thin layer does not eliminate the energy. The shield has to absorb it, redirect it, radiate it, or be destroyed by it. And interstellar travel turns one impact into a statistical problem lasting decades. Most grains are expected to be much smaller than the 1 microgram example. That matters enormously. A spacecraft is far more likely to encounter tiny particles than unusually large ones. The smallest grains may remove only microscopic amounts of material per collision. But the spacecraft is not crossing a laboratory chamber for a few seconds. It is crossing light years. Alpha Centauri is more than 40 trillion kilometers away. A frontal surface moving through that distance effectively sweeps out a long cylinder of interstellar material. Every square meter of exposed area samples that cylinder. Make the ship wider, and it intercepts more material. That creates another trade-off. A large forward shield protects more of the spacecraft. It also presents a larger target. A narrow vehicle reduces the cross-sectional area exposed to dust, but a crewed spacecraft needs volume somewhere behind it. Habitats, storage, radiators, propulsion systems, and redundant machinery do not disappear merely because the nose has been made smaller. The vehicle begins to acquire a directional architecture. A hardened bow faces the direction of travel. Sensitive systems hide behind it. The spacecraft may resemble less a conventional rocket than a long structure traveling behind its own shield. But a shield that survives the beginning of the journey may not have the same thickness near the end. Each impact removes material. Gas bombardment contributes additional erosion. Radiation changes material properties. Thermal cycling continues. The protection system becomes something with a lifetime. That lifetime has to exceed the mission. There are several ways to imagine extending it. The simplest is brute force, carry more shielding. A thick layer of material at the bow could be allowed to erode gradually, with enough reserve that the critical structure behind it remains untouched. Water has sometimes been discussed for radiation shielding in spacecraft because crews need it anyway. But the leading surface of a relativistic vehicle would require a material architecture optimized for hypervelocity impacts as well as particle radiation. Metals, ceramics, carbon-based materials, multi-layer structures, and replaceable sacrificial sections all create possibilities. They also create mass, and the propulsion system has to accelerate every kilogram of protection to 10% of light speed. A shield weighing 100 tons is not just 100 tons of armor. It is 100 tons of armor carrying an enormous kinetic energy bill. Then the ship has to slow that armor down at the destination. So engineers can try another approach. Instead of making the shield indefinitely thicker, move some protection in front of the spacecraft. One concept is to release a cloud of small particles ahead of the vehicle. That artificial cloud becomes a sacrificial region. Incoming dust encounters the forward material first, potentially breaking apart or vaporizing before it reaches the main structure. The idea is attractive because the spacecraft does not have to wait for every collision to occur directly against its hull. But the protection must remain positioned correctly. The particles themselves disperse. The cloud has to travel with the vehicle. Replenishing it requires stored material, and the interaction does not make the incoming energy disappear. It changes where the interaction occurs and what form reaches the ship afterward. Another possibility is active detection. Find dangerous grains before they arrive, destroy them with lasers, deflect them, move the spacecraft. At first, this sounds like a cleaner solution. Then velocity returns to the argument. Suppose a sensor identifies an object 10,000 kilometers ahead. At 10% light speed, the spacecraft reaches that location in about 1/3 of a second. Detection, classification, targeting, and response all have to happen inside that interval. Detect the grain 100,000 kilometers away, and the system gains only a few seconds. And a microscopic dark particle against interstellar space is not an easy target. The larger and more dangerous the grain, the more valuable detection becomes. But large grains are also expected to be rarer, which means the system may spend decades waiting for an event it absolutely cannot afford to miss. Navigation offers little comfort. A starship can steer around planets. It can avoid known stars. It can avoid mapped debris around a destination. It cannot pre-map every microscopic particle distributed across 4 light-years of space. There is no interstellar traffic chart detailed enough to show the path cleared down to grains smaller than sand. The gas cannot be avoided at all. Hydrogen atoms are distributed through the medium on scales far smaller than any navigation maneuver. At 1/10 light speed, a hydrogen nucleus striking the forward surface carries energy of roughly several million electron volts. That places individual particles in an energy regime familiar from ionizing radiation. The gas in front of the spacecraft has not changed. The spacecraft's velocity has changed what the gas looks like in its own frame. This is one of the strangest consequences of fast interstellar flight. The ship manufactures part of its own radiation environment simply by moving. From the perspective of a person floating slowly in the local interstellar medium, the hydrogen is cold and diffuse. From the perspective of the ship, those same particles arrive as a stream of energetic projectiles concentrated almost entirely from the forward direction. Shielding has to handle both the rare violent dust impact and the relentless bombardment of much smaller particles. And when energetic particles enter shielding, secondary effects matter. An incoming proton can collide with atomic nuclei inside the shield. Those interactions can generate secondary particles, electromagnetic radiation, and cascades that transport energy deeper into the material. A sufficiently thick shield can reduce what reaches the crew and electronics. But again, thickness means mass. Magnetic or electric fields offer partial alternatives for charged particles. A sufficiently strong electromagnetic system could influence ionized material before it reaches the hull. That is much less useful against electrically neutral dust grains unless those grains can first be charged or vaporized. Active protection therefore introduces power systems, superconducting magnets, or other field-generating hardware, control electronics, structural loads, and additional failure modes. Protection becomes another machine that must survive the journey. This is the pattern a real starship cannot escape. Passive shielding is heavy. Active shielding consumes power and adds complexity. A smaller spacecraft intercepts less dust but has less room for redundancy. A larger spacecraft protects its crew more easily, but sweeps through more material. Higher speed reduces the years of exposure while making each collision more energetic. Lower speed softens the impacts while extending the mission. There is no velocity at which all of these curves improve together. And dust adds one more problem that may be more difficult than average erosion. The spacecraft does not have to survive the average grain. It has to survive the worst grain it actually encounters. That turns a 40-year flight into a problem of probability. A shield can be designed for what engineers expect. The mission survives only if reality stays inside that design envelope. Somewhere between Earth and another star, the most consequential object the spacecraft ever meets may not be a planet, a comet, or an asteroid. It may be one particle that happened to be larger than expected, and even if the bow survives every one of those impacts, the ship still has to protect something far more delicate behind it. Electronics, sensors, power systems, and, on a crewed mission, living tissue. Because once interstellar gas begins arriving with particle energies measured in millions of electron volts, the front shield is no longer protecting the spacecraft from debris alone. It is protecting the spacecraft from the radiation created by its own speed. The radiation problem begins before a single cosmic ray reaches the crew. It begins at the bow. A spacecraft moving through interstellar hydrogen at 1/10 the speed of light sees those atoms transformed into a concentrated stream of energetic particles arriving almost directly from ahead. The medium itself is sparse, but the ship is crossing it continuously, year after year, while every collision carries far more energy than the same atom would possess in a conventional spaceflight environment. That creates a radiation geometry unlike anything experienced by a spacecraft near Earth. Near our planet, radiation arrives from many directions. Solar particles can come in bursts. Galactic cosmic rays arrive from outside the solar system. A vehicle in low Earth orbit also receives partial protection from Earth's magnetic field and from the planet itself. An interstellar ship has no planetary shield, no magnetosphere surrounds it, no atmosphere absorbs incoming radiation. And at high velocity, the ship adds a new directional component to the environment simply by moving through the gas between stars. The most obvious response is to put shielding in front. That works. But not as cleanly as the word shielding suggests. When an energetic particle enters matter, it does not simply disappear. It collides. It transfers energy. It can ionize atoms, damage molecular structures, displace atoms from their normal positions in a solid, and produce secondary particles deeper inside the shield. A thick protective layer can reduce the radiation that reaches sensitive systems. But a poorly chosen material can also create new radiation inside the structure. High-energy particles striking heavy nuclei may generate secondary neutrons and other fragments. Those secondaries can penetrate farther than expected and deposit energy in electronics or living tissue behind the initial barrier. So the correct question is not how much material the ship can place between the crew and space. It is what material, arranged in what geometry, performs best against the particular radiation field the ship will encounter. Hydrogen-rich materials are attractive for some types of radiation protection because light nuclei can reduce the production of certain damaging secondaries compared with very heavy shielding. Water contains hydrogen, so do many polymers. A crewed starship would already need large quantities of water for drinking, hygiene, food production, and life support cycling. That suggests an architectural strategy. Do not store all of the water in one tank. Place some of it where it can do two jobs. Food stores, water reservoirs, plastics, structural materials, and other consumables can become part of the shielding around inhabited compartments. The ship stops being a habitat placed inside a protective shell. The habitat and the protection become the same system. But this creates another problem. Consumables move. Water is used and recycled. Food mass changes over time. Waste is processed. Equipment is relocated. A shield built partly from mission supplies does not remain identical from departure to arrival. The spacecraft would have to preserve its protective geometry while the material inside it constantly circulates. That is manageable near Earth because radiation shelters can be temporary. An interstellar mission cannot depend on a shelter used only during an occasional solar storm. The forward radiation field follows the ship for the entire cruise. There may be safer regions inside the vehicle, but there is no moment when the basic exposure problem goes away. Then another radiation source enters the picture: galactic cosmic rays. These are high-energy particles moving through the galaxy independently of the spacecraft. Unlike the directional stream created by the ship's motion through interstellar gas, cosmic rays can arrive from many directions. A thick forward shield, therefore, cannot solve the entire problem. The crew needs protection around the habitat. Now, the mass penalty spreads from the nose of the vehicle to the occupied volume itself. Every additional layer increases launch mass. Every additional layer has to be accelerated. Every additional layer has to be decelerated. And if the mission lasts for decades, the shield must protect not only people, but the machinery that keeps those people alive. Electronics do not experience radiation the same way biology does. A human cell can sometimes repair damage. A computer cannot heal a transistor. Radiation can alter stored data. It can flip bits in memory. It can damage semiconductor structures gradually. A single energetic particle can trigger a temporary fault in a circuit that was otherwise functioning perfectly. Modern spacecraft already deal with these problems. They use radiation-hardened components, error-correcting memory, redundant computers, watchdog systems, shielding, software designed to detect and recover from faults. But an interstellar mission changes the timescale. A satellite near Earth may operate for 10 or 20 years. A starship may need critical electronics to function for many decades before arrival. A generation-scale mission could require reliable computation for far longer. Redundancy helps only if failures remain independent. If every backup is exposed to the same radiation environment, aging mechanism, design flaw, or manufacturing defect, multiple systems can degrade together. That means redundancy cannot simply mean carrying 3 identical computers. The ship may need diversity, different hardware architectures, separate physical locations, independent power paths, stored replacement electronics, manufacturing capability, protected archives containing software and design information. At some point, the starship begins carrying not spare parts, but the ability to reproduce spare parts. That is a far more demanding requirement. A failed circuit board can be replaced if another one exists. But after 40 years, how many spares remain? What happens if a component fails that nobody expected to fail? What happens if an entire class of electronics gradually becomes unreliable? A mission that cannot receive physical assistance from Earth needs some form of onboard industrial depth. Machine tools, raw materials, diagnostic systems, fabrication. The ability to manufacture connectors, pumps, seals, pipes, circuit substrates, mechanical structures, and perhaps semiconductor devices. And every layer of manufacturing capability adds equipment. Equipment requires maintenance. Maintenance requires power. Power systems produce heat. Heat must be rejected. Mass grows again. Radiation therefore expands into an industrial problem. Protect the electronics with thicker shielding, and propulsion pays for it. Put the electronics deeper inside the vessel, and the architecture becomes more complex. Use active magnetic fields to divert charged particles, and the spacecraft needs powerful field-generating equipment. That equipment must itself survive. Magnetic protection has an appealing logic. Charged particles respond to electromagnetic fields. If a spacecraft can bend their trajectories before they strike the hull, some radiation could be redirected away from inhabited regions. But the universe does not provide a single clean beam of identical charged particles. There are different particle energies, different charge states, neutral atoms, dust grains, secondary radiation. A magnetic system optimized for one part of the environment does not automatically solve the rest. Strong fields also have consequences for spacecraft design. They can interact with onboard electronics. They require structures capable of tolerating electromagnetic forces. Superconducting systems would require thermal control. A failure in the active shield could expose the vessel to an environment the passive structure was never designed to handle alone. So a realistic design would probably avoid relying on one defensive mechanism. Passive shielding handles what it can. Geometry places sensitive systems behind mass already needed for other purposes. Electronics are hardened, data are duplicated, components are replaceable, some systems may use active fields. The forward structure absorbs the directional punishment created by velocity, and inhabited spaces are buried deeper inside the spacecraft. This changes what a fast starship might look like. Science fiction often gives interstellar ships panoramic windows. A real vehicle moving at 1/10 light speed has almost no reason to place the crew near the forward surface. The bow is the worst place to live. It is where dust arrives, where gas arrives, where erosion is concentrated, where the radiation created by the ship's velocity is strongest. The crew would be safer farther behind the leading shield, surrounded by tanks, machinery, storage, and structural mass. The starship might have no forward windows at all. Cameras can see outside. Radar and other sensors can monitor the path. People do not need direct exposure to space to know where the ship is going. The safest habitat may resemble a protected core buried inside a long machine. That has psychological consequences. For decades, the crew could live inside an enclosed, engineered environment with no practical access to the exterior. Outside the hull is not a place for a spacewalk. At cruise velocity, exposed maintenance becomes extraordinarily difficult. Any repair on the forward side would have to occur behind protection or after the spacecraft slowed dramatically. The ship therefore needs exterior systems designed for remote service, robotic manipulators, replaceable modules, internal access routes, mechanisms that can isolate damaged sections without exposing people. And this leads to another threshold. Eventually, shielding cannot be treated as something fixed at launch. The ship may have to maintain its own protection, inspect erosion, measure radiation penetration, move material, replace damaged panels, reconfigure storage, repair sensors, rebuild parts of the forward structure while still traveling between stars. A starship capable of crossing light years is not simply a vehicle that survives. It is a vehicle that continually restores the conditions required for its own survival. And that distinction will matter even more when the next constraint appears, because all of these systems need power. Not for hours, not for months, for decades. The shield can be thick, the computers can be redundant. The habitat can be buried deep inside the vessel. None of it matters if the spacecraft cannot keep producing energy long enough to reach the destination. Power is what keeps every other system from becoming dead mass. The shield can survive impacts only if sensors continue measuring damage. The habitat can remain stable only if pumps keep moving water and air. Radiation protection can include active fields only if those fields remain energized. Computers can remain redundant only if there is electricity to run them. Manufacturing can replace failed hardware only if machine tools, furnaces, processors, and control systems still operate. A starship traveling for 4 decades does not merely need energy. It needs dependable energy for a very long time. That requirement immediately separates an interstellar spacecraft from almost every machine humans have ever built. Most machines are designed around maintenance environments. Power plants are repaired by large workforces. Aircraft are inspected between flights. Naval vessels enter port. Space stations receive replacement hardware from Earth. Even deep space probes are built with the assumption that once their power supply falls below useful levels, the mission eventually ends. A crewed starship cannot accept that pattern. Its power system is not a component. It is the foundation beneath the entire spacecraft. If propulsion is needed only during acceleration and deceleration, cruise power may be much lower than launch power, but lower does not mean small. A large interstellar vessel might need continuous electricity for environmental control, computation, navigation, medical systems, food production, manufacturing, communications, scientific instruments, thermal pumps, lighting, and repair. And, unlike a spacecraft close to the sun, it cannot depend on ordinary solar panels for most of the journey. At 1 astronomical unit from the sun, solar energy is abundant. Move farther away and sunlight weakens with the square of the distance. Double the distance, and the same panel receives 1/4 of the sunlight. 10 times farther out, it receives 1/100th. Between stars, the sun becomes just another bright point behind the ship. A conventional solar array large enough to support a substantial crew would become absurdly impractical during interstellar cruise. The starship needs an internal energy source. That leaves a narrower set of possibilities. Nuclear fission is mature enough to understand. Radioisotope systems are extremely durable, but provide modest power. Fusion could, in principle, deliver much higher energy density. But controlled fusion power has not yet become an operational terrestrial energy system, much less a decades-long autonomous spacecraft reactor. Matter-antimatter systems offer extraordinary energy density in theory, but producing, storing, and controlling useful quantities of antimatter remains far beyond present engineering capability. Each option creates a different version of the same question. What fails after 30 years? A fission reactor contains fuel, control systems, pumps, heat exchangers, structural materials, neutron absorbers, instrumentation, and electrical conversion equipment. None of those is immortal. High-energy radiation alters materials. Moving parts wear, seals age, coolants can leak, sensors drift, control electronics fail. Corrosion does not care that the nearest repair yard is light years away. The obvious response is redundancy. Install several reactors, run only some at a time, keep others isolated as reserves. If one fails, another takes over. That sounds sensible until the mass penalty is counted. Every backup reactor adds shielding. Every backup adds plumbing. Every backup adds control equipment. Every backup adds structural reinforcement. And all of it has to be accelerated. A starship therefore needs redundancy without allowing redundancy to multiply mass without limit. This is a recurring design problem throughout the vessel. A system with no backup is fragile. A system with 10 complete backups may be too heavy to launch or accelerate. The spacecraft has to find the narrow region between those extremes. Power generation creates another problem that cannot be avoided by clever engineering: waste heat. Every machine that uses energy eventually produces heat. A computer does it, a life support pump does it, a reactor does it, a manufacturing system does it. Even an extremely efficient spacecraft cannot convert all energy into useful work with no thermal consequences. On Earth, unwanted heat can be transferred into air, water, soil, or cooling towers. A spacecraft in vacuum has no atmosphere around it to carry heat away. It must radiate that energy into space. That requires radiators. Radiators are easy to underestimate because they look passive. They are not passive in the architectural sense. They need area, they need plumbing, they need pumps or other means of transporting heat. They need surfaces exposed to space. They must remain within temperature limits. They cannot be hidden behind meters of protective material while still radiating efficiently, and that creates a conflict with the geometry developed for high-speed flight. The safest place for the spacecraft is behind the forward shield. The best place for a radiator is exposed to open space. Those are not the same place. A wide radiator extending sideways from the vehicle increases exposed area. It also becomes vulnerable. Dust striking nearly head-on is the main concern during cruise. So radiators arranged parallel to the direction of travel could reduce their frontal cross-section. But they are still large, delicate structures attached to a spacecraft moving at 30 million meters per second. A puncture in a radiator loop can leak coolant. A warped panel can lose thermal performance. A pump failure can create a local overheating problem that spreads into power electronics or life support. So the spacecraft may need multiple independent radiator loops, segmented panels, valves that isolate damaged regions, robotic repair systems, spare radiator surfaces. The thermal control system begins to resemble another living network that has to heal itself. Now increase reactor power. More electrical capability improves manufacturing, active shielding, computation, and habitat control. But more power means more waste heat. More waste heat requires larger radiators. Larger radiators add mass and exposed structure. Once again, solving one problem enlarges another. This is why a starship cannot simply carry the most powerful reactor available. The useful question is how much continuous power the mission truly needs. Every watt avoided in the habitat is a watt that does not have to be generated, routed, and eventually rejected as heat. Efficiency becomes structural. Low-power electronics reduce radiator area. Good insulation reduces heating demand. Passive environmental control reduces pump loads. Highly efficient motors reduce waste. A civilization building an interstellar ship would probably treat energy economy not as an environmental preference, but as part of propulsion design. The less power required during cruise, the less reactor mass and radiator area the spacecraft must accelerate. But reducing power too aggressively can create fragility. Suppose the ship relies on a single ultra-efficient circulation pump rather than several less efficient pumps. The mass and energy budget improve until that pump fails. Suppose food production is optimized around precisely controlled lighting and nutrient delivery. Energy use falls, but the biological system becomes more dependent on uninterrupted electronics and pumps. Suppose automated repair minimizes crew labor. That saves time. But now the machines that maintain the ship must themselves be maintained. Efficiency can remove margin, and margin is what long missions survive on. This is the deeper challenge of designing for 40 years instead of 4. A component does not have to fail because it was badly made. It can fail because its environment changes slowly. Lubricants degrade, polymers become brittle, metal structures accumulate microscopic fatigue, radiation alters electronics. Thermal expansion and contraction work joints repeatedly. Contamination builds up in fluid systems, sensors become less accurate, the spacecraft ages everywhere at once. A machine on Earth can be rebuilt repeatedly because civilization continuously supplies new materials and replacement parts. A starship has only what it carries and what it can manufacture from that inventory. That means its power system has to support not only daily operation but reconstruction. A pump is replaced. A bearing is machined. A damaged pressure vessel section is repaired. A circuit board is remade. A radiator panel is patched. Each repair consumes stored materials. Some materials can be recycled. Others may become contaminated, irradiated, chemically altered, or simply difficult to recover. Over enough time, maintenance becomes a problem of material accounting. The ship is slowly converting organized hardware into worn hardware, waste, and replacement parts. To remain functional, it must reverse that process again and again. That requires energy. The more capable the onboard industrial system becomes, the more effectively it can fight degradation. But industrial capability also consumes mass, space, power, and labor. Eventually, the distinction between spacecraft and factory begins to disappear. A real interstellar starship may need to be both. And if people are aboard, it must be something else as well. A biosphere. Because machines can be stored cold, shut down, restarted, and replaced. A human crew cannot be turned off for 40 years with any technology we currently possess. Every day of the journey, the ship has to create a small habitable world inside a vehicle moving through an environment that cannot support life for even a few seconds. Power keeps that world running. Heat control keeps the power from cooking it. Repair keeps both systems from degrading beyond recovery. And all of them must continue long enough that the passengers reach another star still alive. That brings the engineering problem inside the habitat. Air, water, food, microbes, waste, and the uncomfortable fact that a closed ecosystem does not fail like a machine. It can fail while every individual component is still working. A closed ecosystem can appear stable right up until the moment its margins disappear. That is what makes life support fundamentally different from most spacecraft hardware. A pump either moves water or it does not. A valve opens or remains shut. A computer can report an error. A biological system can drift for months, while every sensor still reports numbers inside acceptable ranges. Microbial populations change. Trace chemicals accumulate. Nutrients move into places where they are difficult to recover. Plants grow differently from one generation to the next. A contaminant that was harmless at low concentration slowly becomes important, Nothing dramatic happens. Then several small imbalances begin reinforcing one another. A crude starship traveling for 40 or 50 years cannot simply carry enough oxygen, food, and water for the entire journey. The mass would become enormous. The spacecraft has to recycle. Water must be recovered from humidity, hygiene, waste, food processing, and biological metabolism. Carbon dioxide must be removed from cabin air. Oxygen must be regenerated. Nitrogen and other atmospheric gases must remain within controlled limits. Human waste has to become usable material again. Food has to be produced or stored with losses small enough that the crew does not slowly consume the ship's reserves faster than they can be replaced. The central requirement is not perfect recycling. Perfect recycling is impossible. The requirement is keeping losses below the amount of reserve and replace capacity available for the entire mission. That distinction sounds small. Over decades, it becomes everything. The International Space Station already demonstrates how difficult even partial closure can be. Water is recovered and processed. Carbon dioxide is removed. Oxygen can be generated from water. Some waste streams are recycled. But the station is not an independent ecosystem. Cargo vehicles bring food, hardware, gases, clothing, replacement filters, medical supplies, experiments, and spare components. When something breaks, Earth is below. A starship has no cargo schedule. Its life support loop must be more closed than anything humans have operated continuously in space. And the longer the mission, the more dangerous tiny inefficiencies become. Suppose a system recovers 99% of a particular resource during each cycle. That sounds excellent. But 1% loss repeated thousands of times is not excellent. The relevant question is where the lost material goes. Some may remain recoverable in filters. Some becomes chemically bound in waste. Some leaks. Some contaminates machinery. Some becomes incorporated into materials the crew cannot easily process. A closed spacecraft is therefore not only recycling matter, it is constantly searching for matter that has escaped from useful circulation. Carbon offers a useful example. Crew members eat carbon-rich food. Their metabolism converts part of it into carbon dioxide. Plants can absorb that carbon dioxide and use light energy to build new organic material. In principle, carbon moves in a loop, but real ecosystems contain many pathways. Carbon becomes human waste, dead plant tissue, microbial biomass, deposits inside plumbing, volatile organic compounds in the cabin, packaging contamination, material trapped in filters. Every pathway needs either recovery or an allowance for permanent loss. The same is true for nitrogen, phosphorus, sulfur, potassium, and dozens of micronutrients required by plants and humans. A starship carrying a biological food production system is effectively carrying a planetary nutrient cycle compressed into machinery. That machinery cannot assume geology will eventually return missing elements. There's no river eroding a mountain, no deep ocean reservoir. No soil profile tens of meters thick, no atmosphere containing effectively unlimited nitrogen. The accessible biosphere may consist of tanks, growth chambers, pipes, filters, storage bins, and a few thousand cubic meters of controlled habitat. This makes concentrations matter. A chemical imbalance that would disappear into Earth's oceans can become significant inside a closed loop. Trace contaminants from plastics, lubricants, cleaning agents, electronics, plant metabolism, and human activity can gradually accumulate. Some compounds are easily removed. Others may not have been anticipated when the spacecraft launched. A filtration system designed in 1 century may encounter a chemical problem decades later that its designers never tested. The crew needs analytical equipment capable of identifying unknown contamination, not merely sensors tuned to known failure modes. Then biology adds variability. A mechanical filter built to specification behaves within a predictable range until it degrades. Living organisms respond to conditions. Plants alter growth according to light, carbon dioxide, nutrients, temperature, pathogens, and genetic variation. Microbial communities change when their environment changes. Some microbes are essential. Human bodies themselves contain complex microbial ecosystems. Food production, waste processing, and nutrient recycling may depend on microorganisms performing chemical transformations that would otherwise require more machinery. Trying to eliminate microbes from the ship would not produce a cleaner biosphere. It would remove part of the system that keeps the biosphere functioning. The goal is control, and ecological control is more complicated than sterilization. A harmless organism can become problematic if another population declines. A pathogen can enter a crop chamber. Biofilms can grow inside pipes. Microbes can alter materials. A species useful in a waste reactor may be dangerous if it reaches the wrong compartment. The starship therefore needs ecological barriers, much like it needs pressure barriers, separate loops, isolation capability, quarantine, continuous monitoring, stored biological samples, methods for rebuilding damaged microbial communities rather than simply killing them. Agriculture creates the largest biological dependency. Stored food is reliable but heavy. Growing food reduces the amount that must be carried for very long missions, but turns nutrition into an active engineering system. Plants need light. Light requires energy. Plants produce heat and water vapor. Growth chambers need air circulation. Nutrients have to be delivered. Seeds must remain viable. Pollination may need management. Diseases must be controlled. Harvesting and processing require labor or automation. Crop failures no longer mean economic loss. They threaten the atmosphere and food supply simultaneously if plants are also part of oxygen regeneration and carbon dioxide control. That coupling is dangerous. A system that performs several functions efficiently can fail several functions at once. This is the ecological version of the redundancy problem. Using crops for food, oxygen production, carbon dioxide removal, humidity regulation, and psychological benefit looks elegant. But if one disease damages those crops, the starship loses more than calories. So a resilient design would probably separate critical functions. Mechanical carbon dioxide removal should remain available even if plants fail. Stored oxygen reserves should exist even if biological production declines. Food reserves should bridge failed harvests. Multiple crop species should reduce vulnerability to one pathogen. Seed banks should be protected from the environment experienced by the active agricultural system. Efficiency again competes with survival margin. A perfectly optimized ecosystem has little unused capacity. A resilient ecosystem needs excess, extra growing area, extra water, extra nutrients, extra atmospheric processing, extra stored food. All of it is mass. The propulsion system pays again. Human metabolism creates another constraint that cannot be paused. A reactor can be shut down for maintenance if another reactor carries the load. A human population consumes resources continuously. Every day creates carbon dioxide, waste heat, wastewater, biological waste, and demand for food. The crew is both the purpose of the life support system and one of its largest disturbances. Population, therefore, becomes an engineering variable. More people provide more skills, more labor, more genetic diversity, and greater resilience to the loss of individuals. They also require more habitat, more shielding, more food, more water, more oxygen processing, and more medical capability. Fewer people reduce mass, but small populations are fragile. A few deaths can remove unique expertise. Illness can affect a large fraction of the available workforce. Genetic management becomes important if the voyage extends across generations. Social conflicts become harder to escape when everyone inhabits the same closed environment. The spacecraft cannot optimize population only by counting kilograms per passenger. People are part of the redundancy architecture. A surgeon is a capability. So is an electrical engineer. So is someone able to maintain biological systems, manufacture parts, diagnose software, manage power equipment, and train the next person to do the same work. If the mission lasts longer than one professional career, knowledge itself has to be recycled. That may be harder than water. A manual can survive. Competence cannot be stored as text alone. Complex skills depend on practice. A crew that stops using a manufacturing process for 15 years may still possess every instruction required to perform it, and discover that nobody can execute it reliably when the system finally fails. The ship therefore has to preserve not merely information, but institutions of learning, training, Certification, simulation, apprenticeship, repeated practice on systems that may not need repair yet. A generation born in transit would have to learn why procedures exist even though the events that created those procedures occurred before they were born. The spacecraft begins to carry something no ordinary machine requires: continuity of culture. That is where a 40-year voyage and a 200-year voyage become fundamentally different missions. At 10% light speed, nearby stars may be reachable without creating multiple generations aboard the ship if acceleration, deceleration, and human lifespan cooperate. Slow the ship enough or choose a more distant destination, and engineering becomes demographic. The vehicle no longer has passengers who remember departure. It contains a society whose members may never have seen a planet. And once that threshold is crossed, the most difficult system on the spacecraft may no longer be propulsion, shielding, or life support. It may be the agreement, renewed across generations, to keep the mission alive. A generation ship does not fail only when a machine breaks. It can fail while every machine is still working. The air is breathable, the water is clean, the reactors are stable, the shield is intact. The engines remain capable of slowing the vessel at the destination, and yet the mission can still end because the people inside no longer agree on what the mission is. This is a problem ordinary spacecraft have never had to solve. Every crewed mission so far has operated inside a human context that already exists outside the vehicle. Astronauts know where they came from. They know where they are going. Mission control shares the same institutions, language, technical standards, and broad understanding of purpose. Even on a long mission to Mars, the crew would remember Earth directly. A multi-generation interstellar ship changes that. Eventually, nobody aboard has seen the world that launched them. Earth becomes history. The destination becomes expectation. And the spacecraft becomes the only society anyone has ever known. That changes the meaning of mission discipline. The first generation may accept extraordinary restrictions because they volunteered. The second did not. The third inherits a journey that began before they were born and may end after their parents are dead. At that point, the spacecraft is no longer carrying a crew through space. It is carrying a political system, a legal system, an educational system, a culture, a population that has to reproduce not only biologically, but institutionally. That is difficult because institutions also degrade. Procedures that make sense to one generation can look arbitrary to another. Rules written for emergencies may become rituals after the original reasons are forgotten. Authority can become concentrated or fragmented. Technical expertise can become political power because control of essential systems determines survival. A person responsible for the reactor is not simply an engineer. They help control whether the habitat remains powered. A medical team may decide who is capable of reproduction during a demographic crisis. A maintenance authority may decide which section receives scarce replacement material. A navigation council may decide whether the ship should continue toward the original target if new observations suggest the destination is worse than expected. These are not merely technical decisions, they distribute risk. And where risk is distributed, politics appears. The temptation is to imagine that a sufficiently advanced mission would solve this through automation. Let computers manage resource allocation. Let algorithms monitor health. Let artificial intelligence optimize maintenance schedules, population balance, crop production, and navigation. That could reduce some forms of conflict. It would also create a new dependency. Who controls the system that makes the decisions? Who is allowed to override it? What happens if the crew no longer understands its logic? What happens if the software is correct by its original objective, but the society's priorities have changed? A machine can preserve a mission plan perfectly while the humans around it become a different civilization. That is not necessarily failure. It may be adaptation. A generation ship that cannot adapt socially is probably less resilient than one that can. But adaptation creates tension with the reason the ship exists. Suppose the original mission is to settle a planet around another star. Halfway through the journey, the population decides The spacecraft itself is a better home than the destination. They have lived in artificial gravity. They know how to maintain closed habitats. They have no direct experience of planetary life. The destination may contain unknown pathogens, unstable climate, high radiation, or gravity poorly suited to human physiology. Why leave the environment their ancestors spent generations perfecting? From the perspective of the launch civilization, refusing to settle might look like mission failure. From the perspective of the people aboard, it might be the rational choice. This is where the concept of a crew stops working. A crew is expected to complete an assigned task. A society has its own interests. The longer the voyage lasts, the more those interests can diverge from the intent of the people who launched it. That has implications for mission architecture. If success depends on descendants obeying instructions written centuries earlier, the design is fragile. A more robust mission would have to define success more broadly. Survive, preserve knowledge, reach another stellar system if conditions remain acceptable, maintain enough capability to make informed choices. The farther into the future a decision must be executed, the less precisely the launch generation can control it. That is true even without conflict. Knowledge changes. A destination selected because it appears promising from Earth may look different after decades of improved observation. New planets could be discovered in the target system. Atmospheric measurements may reveal unexpected chemistry. A previously unknown stellar companion could complicate orbital stability. A planet once considered habitable may turn out to have a dense atmosphere, no atmosphere, or extreme stellar weather. The starship may learn these things while already committed to the journey. It cannot simply ask Earth what to do. By the middle of a 40-year mission to Alpha Centauri, a round-trip exchange with home takes several years. At greater distances, the delay becomes decades. Earth can provide information. It cannot provide command in the normal sense. That means authority has to move on board. The ship must be able to revise its own mission, and the crew must trust whatever process allows that revision. Trust itself becomes a survival system. A society living inside a closed spacecraft cannot afford unlimited conflict over every resource. Air, water, power, and shielding are shared dependencies. No faction can damage the reactor without endangering itself. No group can monopolize atmosphere indefinitely without threatening the whole habitat. Physical interdependence may encourage cooperation. It can also make sabotage extraordinarily powerful. A person on Earth can damage a local system. A person on a starship may have access to systems whose failure affects everyone. Security therefore becomes unusually difficult. The vessel needs enough access for maintenance, but every access path can become a vulnerability. The crew needs enough technical knowledge to repair the ship. But widespread technical knowledge also means more people understand how to disable it. Highly centralized control reduces some risks. It creates others. If only a small group can operate essential systems, the loss of that group becomes catastrophic. If everyone has access, misuse becomes easier. There is no purely engineering solution because the problem is partly social. The spacecraft must distribute capability without distributing the ability to destroy itself casually. That might require physical separation of critical systems, multiple authorization, independent oversight, mechanical safeguards that do not depend entirely on software, training that emphasizes both competence and responsibility, and institutions capable of surviving leadership changes without losing legitimacy. This begins to sound less like spacecraft design than constitutional design. On a generation ship, the distinction may disappear. The Constitution is part of life support. Education is part of life support. Conflict resolution is part of life support. Mental health is part of life support. Population planning is part of life support. The survival system extends into human relationships. Psychology creates another constraint. People evolved in environments filled with natural variation. Weather changes, landscapes extend beyond sight, sunlight changes through the day. Animals, plants, seasons, smells, sounds, and open horizons continuously alter the sensory environment. A starship is repetitive by comparison, the same corridors, The same rooms, the same machinery, the same limited population, the same external view, if there is one, showing stars that barely appear to move. For decades, artificial environments can be varied. Lighting can simulate day and season. Interior spaces can be redesigned. Virtual reality can provide landscapes. Gardens can create biological complexity. Rotating habitats may provide artificial gravity. None of these reproduces the fact that on Earth, a person can leave one community and join another without leaving the biosphere. On a starship, there is nowhere fundamentally elsewhere to go. Social conflict, therefore, has no geographic escape. A disagreement can persist for years inside the same sealed environment. A family can carry resentment across generations. A small cultural division can grow because there is no outside population to dilute it. This creates another argument for population size. A larger population is heavier, but a larger society is socially more redundant. There are more potential friendships, more professions, more cultural variation, more potential partners, more ways for people to reorganize their lives without remaining trapped inside one tiny network. A smaller crew is efficient in mass, said to be psychologically brittle. Again, propulsion pays for social resilience. Artificial gravity introduces yet another trade-off. Long-term exposure to microgravity causes serious physiological changes. A mission lasting decades would almost certainly need some strategy to provide gravity or counter its effects far beyond what short-duration exercise systems can accomplish. Rotation is one plausible method. Spin a habitat, and occupants experience an apparent outward acceleration. But rotating structures add mechanical complexity. Large radius rotation reduces uncomfortable Coriolis effects, but requires a larger spacecraft. Smaller rotating habitats can spin faster, but rapid rotation may create motion sickness and unusual movement dynamics. Bearings, seals, structural joints, or rotating interfaces must function for decades if the design uses them. Or the entire vessel can rotate, which complicates navigation, radiator placement, and propulsion geometry. Gravity therefore becomes another system tied into architecture, health, maintenance, and mass. There is no compartment called human factors that can be solved independently. People affect the spacecraft affects people, social design affects maintenance, maintenance affects resource allocation, resource allocation affects politics, politics affects whether the mission continues. The engineering diagram has expanded until it contains a civilization, and this leads to a difficult conclusion. The longer an interstellar mission lasts, the less useful it becomes to ask whether the spacecraft can survive. The more useful question is whether the spacecraft can remain a place where people can survive each other. If the answer is no, then increasing reliability of machines only delays the failure. If the answer is yes, then the ship has crossed a threshold no human institution has ever tested. It has become capable of preserving a technical society without access to the civilization that created it. Only then does the next problem matter. Because surviving the cruise is not the same as completing the voyage. After 40 years of shielding impacts, repairing systems, recycling matter, preserving knowledge, and keeping a society intact, the spacecraft still approaches another star carrying the same enormous velocity that made the journey possible. And somehow, it has to get rid of it. A starship traveling at 10% of light speed does not arrive at another star. It arrives with a problem. Velocity. For most of the journey, that velocity is the reason the mission works at all. It compresses 4 light years into a few decades. It reduces the time the crew spends exposed to radiation, mechanical aging, ecological drift, and social instability. Near the destination, the same velocity becomes something the spacecraft has to eliminate. At 1/10 light speed, a ship crosses the distance from Earth to the Moon in roughly 13 seconds. It would pass through the entire inner solar system on a timescale measured in hours. A destination star does not provide enough room for a crewed vessel simply to arrive, notice the planets, and then decide to stop. Deceleration has to begin long before the target system becomes a place the crew can explore directly. And the energy involved is almost the same energy that had to be supplied at departure. For a spacecraft moving well below the most extreme relativistic speeds, slowing down from 10% of light speed requires removing roughly the kinetic energy that was invested in accelerating it. That means propulsion is not one problem. It is two. The launch civilization has to solve acceleration. The starship has to solve braking. If the vehicle carries the energy and reaction mass required for both phases, then everything needed for deceleration must be accelerated during departure. Fuel for braking becomes payload during acceleration. That fuel requires more acceleration energy. If the propulsion system itself is massive, the problem compounds. This is one reason high-performance rocket equations become so punishing for interstellar travel. A rocket does not only accelerate the final spacecraft, it accelerates the propellant that will be used later. And some of the propellant may be required to accelerate other propellant. Chemical propulsion fails this problem almost immediately for velocities anywhere near 10% of light speed. Its exhaust velocity is simply too low. The amount of propellant required becomes absurd. Even advanced nuclear concepts face severe mass ratios unless exhaust velocities rise dramatically. Fusion propulsion changes the scale. It does not make the equation disappear. A fusion engine could, in principle, eject reaction products at far higher velocities than chemical rockets. That improves the relationship between fuel mass and achievable spacecraft speed. But a real fusion system would need fuel storage, confinement systems, power conversion, magnetic structures, heat rejection, shielding, and an engine capable of operating reliably after decades of cruise. The braking engine may spend most of the journey unused. Then, near the destination, it becomes one of the most important machines aboard. That creates a reliability problem, unlike continuous cruise systems. Equipment that operates every day reveals its degradation gradually. A system stored for 40 years may appear healthy until the first time it is asked to deliver full performance. Valves must open, fuel must flow, magnets must energize, control systems must synchronize. Structures must tolerate loads they have not experienced since departure. And if the main deceleration system fails, the crew may have very little ability to improvise. A failed air pump can be replaced. A failed braking architecture may mean the target star passes by while the spacecraft continues into interstellar space. At 30 million meters per second, there is no second approach. The ship cannot turn around in any practical sense and try again. The destination becomes a brief crossing point on a trajectory that continues for light years. This is why interstellar mission design often looks for ways to avoid carrying the entire braking energy on board. One possibility is to use the destination star itself. A magnetic sail is one example. Instead of pushing against conventional propellant, a spacecraft could deploy a large magnetic field that interacts with charged particles in the stellar wind or interstellar plasma. The force is extremely weak, but interstellar journeys are long. A tiny force applied over a large distance can remove significant velocity. A related concept uses an electric sail, extending structures that interact with plasma. Another approach is the photogravitational assist. A very lightweight sail approaching a star could use a combination of stellar photons and gravity to alter its trajectory and reduce speed. For tiny probes, these ideas can be surprisingly powerful. For a crude starship, scale becomes the problem again. A sail large enough to decelerate a massive vehicle may need extraordinary area. That sail has to deploy after decades in space. It has to remain stable. Its material has to survive radiation, dust, thermal stress, and manufacturing imperfections. And if the braking force depends on the destination star's wind or radiation, the mission becomes sensitive to conditions that may not be known precisely when the spacecraft leaves Earth. A magnetic sail also introduces a time problem. Weak braking means braking must begin far away. The starship may start slowing before the target star looks substantially brighter than a brilliant point. The final years of the mission could therefore be spent deliberately giving back the velocity that the launch system worked so hard to create. This reveals a counterintuitive truth. The fastest cruise speed does not automatically produce the shortest mission. Acceleration takes time. Deceleration takes time. If the propulsion system can provide only limited acceleration, a large fraction of the journey may consist of speeding up and slowing down rather than coasting at maximum velocity. The trajectory becomes a balance between peak speed and propulsion capability. For crewed missions, that balance also involves human tolerance. A comfortable continuous acceleration would produce artificial gravity and shorten the time required to reach high velocity. But maintaining substantial acceleration for months or years demands enormous propulsion power and reaction mass unless an external system supplies the force. At 10% light speed, relativity does not yet provide the dramatic time dilation effects associated with much higher velocities. The crew experiences almost the same travel time as observers on Earth. There is no major relativistic shortcut. 40 years remains roughly 40 years. That makes braking especially important because every additional year spent reducing velocity is another year the life support system must survive. Now suppose the ship solves propulsion through an external laser array near Earth. A powerful beam accelerates a sail without forcing the vehicle to carry the launch energy source. For a small probe, this is one of the most compelling known physics strategies for reaching a significant fraction of light speed. But the destination does not automatically contain a matching laser. The spacecraft arrives with the benefit of infrastructure it left behind and none waiting ahead. Acceleration has been outsourced, deceleration has not. This asymmetry is easy to overlook. The first interstellar mission begins from an industrial civilization. The destination is initially empty of infrastructure. A propulsion method that depends on giant stationary machinery may therefore work beautifully for departure and poorly for arrival. That makes the first mission harder than later ones. If a settlement eventually builds large power systems around the destination star, future traffic could use beams at both ends. Ships might accelerate away from one system and be slowed by infrastructure in another. Interstellar transportation begins to resemble a railway network. But before the network exists, one vehicle has to build the first station. That vehicle must carry the disadvantages of a frontier mission. It needs autonomy, manufacturing, power, braking capability, and enough surviving industrial capacity to construct whatever infrastructure future missions will depend on. Arrival, therefore, cannot be treated as the final minutes of the journey. It is an entire mission phase. As the ship slows, the environment changes again. The concentrated stream of interstellar particles created by high velocity becomes less energetic. Dust impacts become less severe. Forward shielding requirements ease. But the destination star becomes more influential. Its stellar wind grows stronger. Its radiation increases. Previously distant planets become navigation targets. The ship has to transition from relativistic cruise architecture to planetary system operations. Systems optimized for 4 light years of straight-line travel may not be optimized for maneuvering among planets. Large forward shields may obstruct sensors. Long radiators aligned with the cruise direction may have to be reconfigured. Rotating habitats may interact with maneuvering forces. Sails may need deployment. Engines dormant for decades need activation. Scientific instruments begin working at levels of detail impossible from Earth. This is the moment when assumptions made before departure meet reality. A planet that appeared promising from dozens of trillions of kilometers away may not be promising at all. Its atmosphere may be too dense or gone. Its surface may be sterile. Its magnetic environment may be severe. Its star may be more active than long-range observations suggested. A planet may contain life. That possibility creates an entirely different problem. A biologically active world is not simply a perfect destination waiting for settlers. It may be scientifically priceless and potentially hazardous in both directions. Earth organisms could contaminate an alien biosphere. Alien chemistry could interact unpredictably with terrestrial biology. Even if direct infection is improbable because the two biospheres evolved independently, biochemical incompatibilities, toxins, reactive compounds, or ecological disruption could make immediate settlement reckless. The mission may arrive after 40 years and conclude that the most responsible action is not to land. A starship, therefore, needs enough flexibility to survive a disappointing destination. Orbital habitats, access to asteroids, mining capability, energy collection. The ability to build rather than depend on a habitable planet. This further increases launch mass. But without it, the mission becomes a wager that observations made from Earth were sufficiently complete to choose a new home. They may not be. The destination system is not the reward at the end of propulsion engineering. It is another unknown environment, and the crew meets it with machinery that has already aged for decades. Imagine the condition of the vessel at that moment. The forward shield has lost material. Some electronics have been replaced. Radiators have been repaired. Reactor components have accumulated operating time. Stored materials have been consumed. The ecosystem has changed. The population may have changed. The people making the arrival decisions may have been children when the ship left Earth, or may not have been born. The starship that arrives is not physically identical to the one that departed. It is the surviving version of that ship. Now the engines ignite, or the sail deploys, or the magnetic field expands, and the spacecraft begins paying back its velocity. For years, perhaps, the destination star grows brighter while the ship slows. Only when the energy of interstellar cruise has been sufficiently removed does another star system stop being something the spacecraft is passing through. It becomes somewhere the spacecraft can remain. That distinction is the difference between reaching another star and actually arriving there. And even after the ship has stopped, the mission is not finished. The propulsion problem has ended. The survival problem has changed location. Stopping near another star solves only one problem. The ship is no longer racing through interstellar space. It is still carrying a population that has no external supply chain. For decades, the spacecraft survived by consuming reserves, repairing itself, recycling material, and protecting a closed environment from damage. Arrival does not restore the world that supported it. There is no port, no warehouse, no electrical grid, no medical industry, no factory capable of replacing an entire reactor, no launch complex waiting to send assistance. The Starship has reached another planetary system, but from an engineering perspective, it is still alone. That makes the first years after arrival potentially more dangerous than the cruise. During the voyage, the environment was hostile but comparatively simple. The ship knew the direction of travel. The major loads were predictable. Its systems operated inside a configuration designed before departure. At the destination, almost everything begins changing. The vehicle must maneuver, survey, mine, build, deploy power systems, establish new habitats, process unfamiliar materials, and decide where its population can safely live. Every one of those activities consumes machinery that may already be decades old. The ship arrives not as a finished settlement, but as the industrial seed from which one has to grow. That distinction matters. A spacecraft can survive by preserving itself. A colony survives by increasing what it can make. At first, the safest choice may be not to descend to a planet at all. A large asteroid or small moon can offer raw material without demanding that the settlers immediately confront an unknown surface environment. Low gravity simplifies extraction and transport. There may be metals, silicates, carbon-bearing compounds, water ice, other volatiles. Exactly which resources are available depends entirely on the target system. Remote observations from Earth can help identify prank bodies. They cannot provide a complete inventory. The first mining operation therefore begins as reconnaissance. Robotic vehicles examine composition. Samples are processed. Materials are tested against the manufacturing systems carried aboard. Only then can the settlement discover whether the local environment contains what its industrial plan assumed it would contain. This is a dangerous place for optimistic design. Suppose the Starship expects to obtain water from nearby asteroids. Then the accessible objects turn out to contain less water than expected. Suppose its metallurgy is optimized for certain ores. Local material contains troublesome impurities. Suppose carbon, nitrogen, phosphorus, or another biologically important element is much harder to acquire than predicted. The mission may possess enormous quantities of rock and still lack one element needed to expand the biosphere. Abundance is not the same as usefulness. Earth's industrial system relies on a planetary network of deposits, chemical processing, transportation, specialized equipment, and centuries of accumulated knowledge. A new settlement has to compress that network into something much smaller. It needs to turn raw material into structural metal into pressure vessels, minerals into glass, chemical feedstocks into polymers, semiconductor materials into electronics, ice into water and propellant, waste back into industrial input. Every step requires energy, every process requires equipment, and every machine used to build new machines is itself a point of failure. This is the bootstrap problem. The colony cannot become self-sufficient merely by carrying a list of blueprints. It needs a chain of manufacturing capabilities complete enough to reproduce the parts that reproduce the other parts. A lathe can make many mechanical components. It cannot manufacture an advanced microprocessor. A chemical reactor can produce useful compounds. It cannot replace a cracked pressure vessel without metal-forming equipment. A metal printer can fabricate complex shapes. It cannot create feedstock unless another system refines the raw material. Industrial independence is not one machine. It is a network. The more complete that network becomes, the less the colony depends on equipment launched from Earth. But completeness has a cost. The first starship cannot carry an exact copy of terrestrial industry. It has to decide what capabilities are essential enough to bring, what can be manufactured later, and what technologies should deliberately be simplified because simpler systems are easier to reproduce. That last possibility is easy to overlook. The most advanced machine is not always the best machine for an isolated settlement. A component built on Earth may achieve extraordinary efficiency by relying on microscopic tolerances, specialized alloys, complex electronics, and supply chains distributed across several countries. A colonial version may be less efficient but easier to manufacture locally. A pump that consumes more power but can be rebuilt in a small workshop may be more valuable than a highly optimized pump requiring a component the settlement cannot reproduce. A rugged electrical motor may outlast a more sophisticated design. A computer architecture based on older fabrication technology may be preferable if the colony can eventually manufacture it itself. Interstellar settlement could therefore force a temporary technological reversal. Not abandonment of knowledge, reduction of dependency. The colony may possess scientific understanding far beyond early 21st century Earth, while intentionally using some machines that are easier to repair, understand, and reproduce. Technology becomes successful not when it is maximally advanced, but when the entire system can support itself. Power is the first requirement. During cruise, the starship carried whatever reactors or other energy systems kept the habitat alive. At the destination, energy demand increases dramatically. Mining requires power, refining requires power, manufacturing requires power, construction requires power. If the settlement begins producing propellant, running large furnaces, processing kilometers of material, or building habitats, its energy requirements may quickly exceed cruise demand. The local star now becomes useful again. Solar collectors can operate effectively if the settlement is close enough and the star's output is suitable. Unlike the cruise vehicle, the colony can spread collectors across enormous areas without accelerating them to interstellar velocity. Area is no longer as expensive. This changes the mass equation. Structures that would have been impossible to carry at departure can be built from local materials once the settlement has enough industrial capacity. Large radiators, storage habitats, TATs, solar communication dishes, rotating settlements. Its destination system begins providing the mass that propulsion prevented the starship from carrying. In principle, this is the moment the mission becomes easier. In practice, it creates a vulnerable transition. The settlement has to construct local infrastructure before the aging ship becomes unable to support it. Too slow, and the colony remains dependent on systems that have already accumulated decades of wear. too fast, and it risks exhausting reserves or damaging equipment through aggressive use. The spacecraft becomes a temporary bridge. Its reactors keep the first workshops running. Its habitat protects the first workers. Its medical facilities support the population. Its stored materials cover gaps in local production. Every year, some of those roles must move away from the ship. First power, then water processing, then manufacturing, then agriculture, then habitation. Eventually, the colony has to reach a point where losing the original starship would no longer mean losing the settlement. That may be the true arrival. Not orbital insertion, not landing. Independence. And independence may take decades. Imagine the psychological change inside the population. For most of their lives, conservation defined survival. Every kilogram mattered. Every spare part had a history. Every material loss reduced a finite reserve. Then local industry begins producing tons of structural material. Water tanks expand. New living volume opens. For the first time since departure, the physical world available to the population grows. Children can enter habitats that did not exist when their parents arrived. Machinery can be built rather than merely preserved. The civilization begins accumulating instead of only maintaining. But expansion also creates new failure modes. More habitat requires more atmosphere. More population requires more food. More industry increases power demand. More mining creates more machinery to maintain. New settlements can become physically separated from one another. The society that survived because everyone depended on one ship may fragment as different habitats acquire their own resources and priorities. The first successful colony, therefore, does not escape complexity. It creates it. And if the long-term objective is not merely to survive around one new star, but eventually to continue farther, another threshold appears. The settlement must build an interstellar spacecraft, not repair the one that brought it, build another, using local industry. That is a much stronger test than arrival. It requires the colony to reproduce propulsion systems, shielding, reactors, habitats, electronics, manufacturing equipment, and every other capability that made the original mission possible. If it can do that, then interstellar expansion becomes self-propagating. One technological system has crossed the distance and recreated the ability to cross it again. If it cannot, the colony may still prosper for thousands of years. But the expansion wave stops there. This distinction changes the usual picture of a galaxy filling with civilizations. Colonization does not require merely surviving one voyage. Every new system must eventually rebuild the industrial depth required for another. Every link in the chain has to work. A civilization might cross 4 light years and discover that maintaining a settlement is practical while building the next starship is not. It might decide that repeating the journey is too expensive. Its descendants might have no interest in leaving. The galaxy does not fill because one starship succeeds. It fills only if success reproduces itself, and now the original question has changed again. At 10% of light speed, the challenge was supposed to be distance. Then it became dust. Radiation power, heat, ecology, maintenance, society, braking, arrival. Now, even after reaching another star, the mission faces one final engineering test. Can a spacecraft deliver not just people, but enough civilization for those people to stop needing the spacecraft? By this point, 10% of the speed of light no longer looks like a number on a propulsion chart. It looks like a design decision that reaches into almost every part of the mission. Go faster, and the voyage becomes shorter. The crew spends fewer years inside a closed environment. Machines have less time to age. The political system has fewer generations to preserve. The destination is reached before more knowledge, institutions, and biological systems have time to drift. But the spacecraft pays for that reduction in time with energy, with shielding, with impact severity, with more demanding braking, with tighter tolerances on navigation and protection. Go slower, and those problems soften. Dust impacts become less violent. The kinetic energy that must be created and later removed falls dramatically. Protective systems can be lighter. Braking becomes easier. But the ship now has to function longer. A mission that takes 40 years may still be completed by people who remember departure. A mission that takes 200 years is a different category of project. At that point, the problem is no longer how to transport a crew. It is how to preserve a technical civilization in motion. This means there may be no universally best interstellar speed. There may only be a speed that minimizes the total difficulty of a particular mission. That optimum would depend on propulsion, shielding technology, destination distance, crew size, reliability, power generation, life support closure, artificial gravity repair capability, and how much risk the launch civilization is willing to tolerate. Speed is only one variable inside the system. This is a major correction to the way interstellar travel is usually imagined. The fastest ship is not automatically the best ship. In aviation, higher speed can shorten exposure to weather and reduce travel time while remaining inside infrastructure designed to support the aircraft. In interstellar space, increasing speed changes the physics of the environment itself. The spacecraft becomes harder to protect at the same time that it becomes easier to keep alive for the required duration. The mission is therefore an optimization problem with competing curves. Some become worse with time, others become worse with velocity. The practical solution may lie where neither side is comfortable. Perhaps 10% of light speed is too fast for a heavily crewed vehicle, but reasonable for small robotic probes. Perhaps a large starship would travel more slowly and accept a longer voyage in exchange for lower shielding and propulsion demands. Perhaps the first serious interstellar missions would not carry humans at all. That possibility deserves attention because robots alter almost every constraint. A robotic probe does not need breathable atmosphere. It does not need food. It does not need psychological stability. It does not require artificial gravity. Its electronics can be shut down or placed in low power states for portions of the journey. It can tolerate accelerations that would be unacceptable to a crew. It can be smaller, which reduces cross-sectional area and therefore the amount of interstellar material intercepted. A civilization trying to reach another star may therefore begin by sending machines long before it sends people. And those machines could change the later mission. A precursor probe might enter the target system decades before a crewed vessel departs. It could map planets more precisely, measure stellar activity, examine asteroids, determine resource abundance, study radiation, search for biology, identify safe orbits, perhaps even begin constructing infrastructure. This creates a radically different mission architecture. Instead of sending a starship into an almost unknown system, send information first, then send machines, then send construction capability. Only then send people. The distance remains the same. The risk distribution changes. A robotic precursor can fail without killing a crew. If it discovers that the target system is unsuitable, the larger mission can be redirected or canceled before departure. If it succeeds, it can reduce uncertainty at the destination. The first inhabited starship might arrive to find navigation beacons, power systems, automated mines, communication equipment, and stored materials already waiting. That would transform braking and settlement. A powerful destination side laser or other beam infrastructure could help decelerate incoming craft. Local factories could begin producing shielding and habitat structures. Robotic observatories could update maps continuously. The crewed ship would no longer have to carry every solution with it. But now another timescale appears. To build infrastructure before humans arrive, the precursor must leave earlier, potentially much earlier. If a robotic mission takes 50 years to reach the system, then another 20 or 30 years are required to survey and construct useful equipment. The human mission may begin planning around events, extending beyond the careers of the engineers who launched the first probe. Interstellar exploration becomes an institutional project, measured in generations even when the human flight itself is not. That may be one of the most difficult barriers of all, not physics. Continuity of investment. A civilization must begin something whose most important results may occur after its original decision-makers are gone. Budgets change, governments change, economic priorities change, technologies change. New discoveries may make the original design obsolete before it reaches its destination. An interstellar program, therefore, needs not only durable spacecraft, it needs durable commitment. This is another reason modularity matters. A rigid mission designed around one technology can become trapped by its own timescale. A more flexible program could send multiple generations of probes. The first maps the target, the second carries improved instruments. Later vehicles travel faster and may overtake earlier ones. Information arriving from the system updates the designs of missions still being built near Earth. Interstellar exploration becomes a sequence rather than one heroic launch. That pattern is already familiar in planetary science. We did not learn the solar system with one spacecraft. Flybys came first, then orbiters, landers, rovers, sample return missions. Each mission reduced uncertainty for the next. The same logic would be even more valuable across interstellar distances because mistakes cannot be corrected quickly. A civilization serious about sending people to another star would probably want an evidence chain before committing human lives. Which star is stable enough? Which planets have useful environments? Where are the accessible volatiles? How strong is the stellar wind? What is the density and grain distribution along the route? Where should braking begin? What local materials can be processed? What forms of life, if any, already exist there? Each answer can remove mass from the human mission. Knowledge is one of the few things that can replace hardware without adding kilograms. If a destination is poorly understood, the starship must carry options. Multiple landing systems, larger reserves, more shielding, more industrial flexibility, more contingency equipment. If the environment is known in detail, the design can become more specific. Better information reduces uncertainty. Reduced uncertainty reduces required margin, and lower margin can reduce mass. This is why astronomy itself becomes part of propulsion engineering. A more capable telescope on Earth can indirectly make a future starship lighter. So can a precursor mission. So can better measurements of the interstellar medium between the stars. The fastest path to another star may therefore begin by remaining at home long enough to understand the route. That creates a final paradox. Every decade spent improving propulsion might increase eventual cruise speed. Every decade spent improving life support might reduce the mass of the habitat. Every decade spent improving autonomous manufacturing might make the ship more repairable. Wait long enough, and the mission becomes easier. But if every generation waits for the next technology, departure never occurs. A real interstellar program would eventually have to choose a moment when the design is good enough, not perfect, good enough to survive. That decision would be made under uncertainty. No experiment on Earth can run a 40-year interstellar voyage through the actual interstellar medium. No habitat test can reproduce every biological and social condition of a multi-generation mission. No accelerated aging program can reveal every failure mechanism that appears after decades of operation. Some risks can only be reduced by building experience. That may favor a progression of increasingly ambitious missions. First tiny probes, then larger autonomous craft, then vehicles capable of complex repair, then perhaps biological payloads. Only after enough of those systems survive does a crude starship stop being one giant leap and become the next step in an engineering sequence. This changes what the phrase interstellar civilization should mean. It does not begin when a species invents an engine powerful enough to reach another star. It begins when the species builds a chain of systems capable of continuing without immediate support from home. Propulsion is the entrance requirement. Everything after propulsion decides whether the journey counts. At 10% of light speed, the destination may be only decades away. But the civilization that launches the ship has to solve problems whose roots extend through materials, science, thermodynamics, ecology, computation, manufacturing, medicine, sociology, and long-term governance. The spacecraft is not a faster version of anything we already possess. It is an artificial world that must remain technically competent while carrying enough energy to cross interstellar space and enough knowledge to rebuild itself when it arrives. The speed is extraordinary. The harder achievement is continuity. And that is why the deepest limit on interstellar travel may not be the distance between stars. It may be the amount of civilization that has to survive the distance with us. At 10% of the speed of light, the nearest star is not unreachable. That may be the most important distinction to preserve. Nothing in known physics places a wall at that velocity. A spacecraft can, in principle, move that fast. The difficulty is what has to move with it. Shielding, power, heat rejection, radiation protection, life support, manufacturing, medicine, computers, spare capacity, food production, a political system, a body of technical knowledge, and, if people are aboard, a population capable of keeping all of those systems functioning for decades without physical help from Earth. The engine is only the beginning. That is why asking whether humanity could build a starship capable of reaching 10% of light speed produces a misleadingly simple picture. A propulsion system can be described by thrust, exhaust, velocity, energy, and mass. A surviving starship cannot. It is a network of compromises. Increase the speed and the journey gets shorter, but interstellar gas becomes more energetic. Dust impacts become more destructive. Shielding requirements rise. Braking becomes more demanding. Reduce the speed, and the hull has an easier crossing. But the ecosystem must live longer. The reactors must operate longer. The crew must remain healthy longer. The society must preserve purpose longer. There is no setting where all of those problems become small at once. That may be the real physical meaning of interstellar distance. Distance does not merely demand speed, it demands endurance. Endurance has mass. Consider the vehicle after departure. Its propulsion system has already spent an enormous amount of energy creating its velocity. Ahead of it is a region that looks almost empty. A telescope would show darkness. A person looking through a camera might see little more than stars, yet the bow is being continuously struck by matter. Hydrogen, helium, microscopic dust. Particles that would be insignificant to a slowly moving spacecraft arrive with energies created by the starship's own motion. The shield loses material. Electronics accumulate radiation damage. Sensors monitor a route that cannot be mapped grain by grain. Behind the shield, machines keep a small volume of matter organized into something Earth-like enough for humans to survive. Water moves through pipes, carbon moves through air, crops, people, waste systems, and back again. Heat moves toward radiators, power moves through cables, information moves between computers and generations. Every loop must remain closed enough, not perfectly closed, just closed enough that the losses do not become fatal before arrival. That phrase may define the entire mission. Good enough for long enough. No individual component has to be immortal. The spacecraft has to remain capable of replacing what is not. That suggests that the most valuable technology on a real starship may not be the engine, it may be repair. A machine that can diagnose unfamiliar failures. A factory that can make replacement hardware from a limited inventory. A software archive that remains understandable after decades. A training system that preserves skills after the original experts are gone. A habitat that can isolate one ecological failure before it contaminates everything else. A power system with enough reserve to survive the loss of part of itself. A society able to change procedures without losing the knowledge of why the procedures existed. The starship survives not by avoiding failure. It survives by containing failure. That is a different engineering philosophy from building the strongest possible machine. It means accepting that parts will wear out, sensors will drift, materials will degrade, people will make mistakes, crop systems will occasionally fail, political disagreements will occur, unexpected events will happen because 40 years is too long for every event to be predicted. Resilience is the ability to absorb those surprises without allowing one of them to become final. Then the destination approaches. After decades spent protecting velocity, the spacecraft begins destroying it. Its braking system takes over. The star ahead becomes brighter. The interstellar particle stream weakens as speed falls. Objects that once existed only as remote measurements become worlds. Some may be useless, some may be dangerous, some may contain resources, one may contain life. And the crew may discover that the mission imagined on Earth is no longer the mission that makes sense there. A successful starship, therefore, has to arrive with choices. It needs enough capability to survive without a perfect planet, enough industry to use asteroids and moons, enough energy to construct new infrastructure, enough scientific independence to decide whether a world should be settled, studied, protected, or avoided. Only after the settlers can make power locally, process local material, expand habitats, produce food, manufacture essential parts, and survive without the original vessel has the journey truly ended. Everything before that is still transportation. There is a useful way to measure the scale of the achievement. A spacecraft reaches another star when its trajectory gets there. A civilization reaches another star when it no longer needs the civilization it came from to remain alive. That second event is much harder. It is also the point where interstellar expansion could become repeatable. If the new settlement can eventually build another starship, then one crossing can become two, then four, then perhaps a network of inhabited systems separated permanently by years of communication delay. But even that future would not resemble a single empire spread smoothly across the Milky Way. Distance would remain. Local autonomy would remain. Physics would remain. No propulsion system removes the speed of light from communication. No shield makes matter harmless at arbitrary velocity. No technology makes energy free. No civilization becomes exempt from maintenance. The stars may become reachable without becoming close. That is perhaps the most important correction to the dream of interstellar travel. Reaching Alpha Centauri at 10% of light speed would be one of the greatest engineering achievements in human history. It would not mean humanity had conquered interstellar space. It would mean we had learned how to keep one artificial world alive long enough to cross a tiny fraction of it. Beyond Alpha Centauri would still be thousands of other stars separated by similar distances. Beyond them, tens of thousands more. The Milky Way would remain enormous. Interstellar travel would become possible without becoming easy. And perhaps that is the realistic frontier. Not faster than light ships. Not effortless jumps between worlds. A machine moving through ordinary space, obeying ordinary physics, carrying everything required to remain a living technological system, while Earth slowly becomes another star behind it. At the beginning of this journey, 10% of the speed of light looked like the solution. Then a microscopic grain of dust appeared in the path. That grain revealed the deeper rule. At interstellar velocity, nothing stays small. A particle becomes an impact problem. An impact problem becomes a shielding problem. Shielding becomes mass. Mass becomes energy. Energy becomes heat. Heat becomes radiator area. Longer travel becomes maintenance. Maintenance becomes manufacturing. Manufacturing becomes power. Life support becomes ecology. Ecology becomes society. And society becomes part of the spacecraft. The distance to another star is measured in light years. But the difficulty of crossing it is measured in everything the ship must continue to be when it gets there. At 10% of light speed, empty space does not become impossible. It becomes expensive in every form that matters. And if one day a human starship really does cross that darkness, the most extraordinary thing about it may not be how fast it moved. It may be that, after decades between stars,